This Zoom session is being brought to you by the fractal odd dyadic horizon. This is one I made up only this last year or so. I think it's really original. Well, whatever. All right, for today, we're going over trigonometric identities. These are like trigonometric equations, only they're true for all values of x, not just for some. So you don't solve an identity, you use it to use identities to solve equations. So, okay, there are a few we've already seen a fair amount of. The ratio identities, tan equals sine over cosine, cotangent equals tangent over cosine over sine. Therefore, the reciprocals of each other. Secant is reciprocal cosine, cosecant is reciprocal sine. That's by the definition of those. And really, that's what identities are. They go on about the identity, about definitions. Because the cos by sine is on the unit circle, therefore sine squared theta plus cos squared theta equals 1. And there are related ones. This is the one I usually use. There are a couple others which exist, also called trigonometric identities. They aren't used as often because they're a little harder to remember. If you divide throughout by tan squared, you get tan squared plus 1 equals sec squared. If you divide throughout by sine squared, you get 1 plus cotangent squared equals cosecant squared. My difficulty with these is that I have trouble remembering which is 1 plus which. Tan squared plus 1 is sec squared, or sec squared is plus 1 is tan squared. I forget which. It's this. It's hard to remember. There are also parity identities where you change theta to minus theta and what happens to the trig functions. Cosine and secant take negative theta and get you the same thing as before, cos theta and secant theta. I like to say that cosine and secant absorb a negative. These are also known as even functions. Odd function is the one which transmit a negative. The negative comes out from inside the trig function to outside. So sine of negative theta equals negative sine theta. Cosecant of negative theta is negative cosecant theta. Tangent of negative theta is negative tan theta. And cotangent of negative theta is negative cotangent theta. There's also co-function identities between trig and cotrig. Cosine of theta is sine of the complement, pi halves minus theta. Sine of theta is cosine of the complement, pi halves minus theta. Tangent theta is cotan pi halves minus theta. Cotangent theta equals tangent pi halves minus theta. Secant theta equals cosecant of pi halves minus theta. And cosecant theta equals secant of pi halves minus theta. In general, trig theta equals cotrig of pi halves minus theta. Trig theta equals cotrig of co theta. In other words, the complement of theta. Now, all right. We use these identities to prove other identities. We'll be finding others along the way pretty soon, the angle addition formula and some such. However, and this is one of the few parts of the book where I will actually insist that I see the steps for you to derive an answer rather than just say the answer. So let's say prove such and so. All right. It will not do just to say yes, that's true. I need to show some steps, and there are some details about how to present it. There are right ways to prove an identity, and there's a wrong way. Please don't use the wrong way. Here's how it works. One way to prove an identity, to prove A is identical to Z. We use 3 lines to prove mean identical. You start by direct simplifying A, and after a number of simplification steps, you wind up with the other. A is identical to B is identical to C all the way down to Z. So therefore A is identical to Z. That's the simplest way. You start with one and simplify it down to the other by using the trig identities. A little bit more common, a little easier, is you take both A and Z and simplify them both down to the same thing. Therefore, A is identical to Z. So, for example, 1 plus tan squared equals sec squared. Prove that. Well, 1 plus tan squared, 1 is cos squared plus cos squared over cos squared, plus tan squared is sine squared over cos squared. Okay, we add these fractions by adding them numerators over a common denominator. Cos squared plus sine squared over cos squared. This on the numerator is just 1. Is identical 1 over cos squared, and that's sec squared theta. QED, we're done. We started the left side and reduced it to the right side. Okay, the second method here, we have 1 plus tan V over 1 minus tan V. Prove that it's identical to cotangent V plus 1 over cotangent V minus. We'll take both of these and we'll reduce them to the same thing. Thus, 1 plus tan over 1 minus tan. Well, tan is sine over cosine. here and here. Multiply the fraction above and below by cosine, and get 1 times cosine is cosine, plus sine times over cos times cosine is sine. Here the denominator, cosine times 1 is cosine, minus cosine over cos times cosine is sine. So the left side is cos v plus sine v over cos v minus sine v. Now the right side, cotangent v plus 1 over cotangent v minus 1. We'll write cotangent as cosine over sine, here and here. Then we'll rescale, multiply above and below by sine. And after appropriate multiplications, you get cosine v plus sine v over cosine v minus sine v. But these are identical. They're the same thing. Therefore, the left side is identical to the right. And we're done. Okay. Now, so here are the two main methods of proving it. Reduce one to the other directly, or reduce both to the same thing. One way, please, do not use this. I've seen it so often. Do not treat an identity as an equation that you have to solve. So I've seen people do this. They'd start by assuming the identity is true, and from it derive the identity. So, okay, so what you do is you would start by saying, you assume that this is true. Then you transpose and you do this, that, and finally get, like, say that sine squared equals sine squared. Well, that proves nothing. Just because you can derive an identity from assuming an identity doesn't prove the identity, because you can have a false statement and derive from it a true statement. For example, you could assume that -1 is 1. Then you square both sides, you get 1 equals 1, which is true, but it was implied by a statement which was false. So that's not a valid proof method. I hesitate to actually go through this, but to give an example, because you might take that as something to emulate. But again, the idea is that this false method would start by stating an identity, and then using algebraic equations, algebraic procedures to reduce it to another identity, not a proof. To repeat, the correct way to prove it is to take the left side and reduce it to the right side by steps, or take left and right side and reduce it by steps, then both by steps to the same thing. So for example, here's an identity. Prove that 3 sine squared theta plus 4 cosine squared equals 3 plus cos squared theta. All right, we start with the left side, 3 sine squared plus 4 cos squared. Well, this 4 cos squared is 3 cos squared plus cos squared. So it's 3 sine squared theta plus 3 cos squared theta plus cos squared theta. Now these two terms, 3 sine squared plus 3 cos squared, have a common factor of 3. So you get 3 times sine squared plus cos squared, that plus cos squared. Oh, but what do you know? Sine squared plus cos squared equals 1. So you get 3 times 1 cos squared theta. And that is the right-hand side, and the identity is thereby proven. Or here's tan squared minus cotan squared over tan theta plus, tan theta plus cotan theta over tan theta plus cot theta. Prove that it is identical to sine squared theta minus cos squared theta. All right, now the left side, we'll write the tangent as sine over cosine. The cotangent is cosine over sine. We'll rescale the equation by multiplying above and below by sine times sine. Sine over cosine times cosine is sine squared, minus. Cos over sine times cosine is cos squared. Here, this times this is sine squared, plus this times this is cos squared. Sine squared minus cos squared over sine squared plus cos squared. But this denominator equals 1. So you get sine squared minus cos squared equals 1, and that equals the right side. Therefore, the left side is identical to the right side. That's a proof. All right. Okay. Right. Now, later we will be seeing other identities such as, oh, before I go on, yes. I've included in the modules this thing I found on the web. I found it so charming, I put it up. It's called the super hexagon for trigonometric identities. It looks like this. It looks like a hexagon with a 1 in the center. Tan, sine, cosine, cotangent, cosecant, and secant. All right. Things that are opposite from each other, across from each other, are reciprocals. Tan times cotangent equals 1. Sine times cosecant equals 1. Cosine times secant equals 1. Therefore, they're reciprocals of each other. So this neatly mentions the reciprocal relations. Also, if you have 3 in a row, A, B, C, then the outer ones multiply to the inner one. A times C equals B. So A is B over C and C is B over A. So you can read it as a fraction. A equals B over C, C equals B over A. So for example, tangent equals sine over cosine. Sine equals cosine over cotangent. Cosine equals cotangent over cosecant. Cotangent equals cosecant over secant. Cosecant equals secant over tangent, and secant equals tangent over sine. And conversely, cosine is sine over tangent, sine equals tangent over secant, and so on around the circle the other way around. So you have these these multiplication and ratio identities. Okay, we also have co-trig identities. If you flip through this vertical line, you turn a function into its complement, 90 degrees minus the other. Sine is cosine of 90 degrees minus theta. Tangent theta equals cotangent of 90 degrees minus theta. Secant theta equals cosecant of 90 degrees minus theta. So you get this co-trig identity. Now, for the Pythagorean identities, you get a little more complicated thing, where 3 of the triangles have a kind of a circle. A squared plus B squared equals C squared. So, for example, sine squared plus cos squared equals 1 squared, and 1 squared plus cot squared equals cosec squared, and tan squared plus 1 squared equals sec squared. So these are the various trig identities summarized in this diagram. I give it to you for your convenience. I think it's kind of cool. And later we'll be going on to more identities, such as the sum and difference identities. Trig function of alpha plus and minus beta equals what? And it'll turn out to be you can write it in terms of trig functions. And we'll see much more about that as time goes on. Okay, I think that's sufficient for today. Stop.